All right, let's get back to talking about trends in physical properties on the periodic table. In the last video, we looked at atomic radius, and we looked at a couple of different concepts as to why the trends in atomic radius are what they are, namely nuclear charge, electron shielding, and effective nuclear charge. Now what we're going to do is look at the concept of ionization energy. Ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. You may remember that a mole is a unit of quantity in the SI system. But for right now, really all you need to think about this is conceptually, ionization energy is the energy required to generate a cation from an atom. How much energy does it take to remove electrons? And the idea here is whether or not an atom wants to gain or lose electrons. So let's look at some trends on the periodic table. As you move from bottom to top in a group or top to bottom, you can look at it either way, ionization energy increases. Well, let's think about this. Lithium, if a lithium is going to lose an electron, where's it going to lose that electron from? Well, its highest energy electrons are in the 2s. Electrons are always going to come out of the highest energy levels because they're the ones furthest away from the nucleus. The most amount of electron shielding, so they feel the least amount of pull to the nucleus. But let's go down to cesium, which is in the 6th period, so its electrons are in the 6s. So the electron that cesium is trying to lose much further away from the nucleus than lithium. And there's a tremendous amount of electron shielding between that 6s electron and all the other electrons in the lower energy levels. So in terms of losing an electron, it's going to be much easier for cesium to lose an electron than it's going to be for lithium to lose an electron. Let's talk about going across a period. Again, nuclear charge is increasing, but there's not a significant amount of increase in shielding. So as you move across a period, it gets harder and harder to take an electron away from an atom. Furthermore, think about the very last row on the periodic table, the noble gases. Noble gases have the lowest possible arrangement of electrons. And so they are incredibly stable and they do not want to lose electrons. It is very hard to take an electron away from a noble gas. Fluorine, on the other hand, would tend to want to gain an electron in order to get to a noble gas electron configuration. And so going to be very difficult to take an electron away from fluorine because fluorine is already super close to a noble gas, and by gaining one, it can get there. On the other hand, if we go to our alkali metals, the first group on the periodic table, all the way on the left, lithium or sodium or potassium each only need to lose 1 electron to get a noble gas electron configuration. So we would expect their ionization energies to be fairly low. Here's some really nice tables that describe some of these trends. So we start with hydrogen, which typically is more inclined to gain an electron than lose an electron, but it has kind of a middling ionization energy there because it could technically do either. Helium, on the other hand, is a noble gas, incredibly stable, full 1s sublevel, and so it has a very high ionization energy. And then you drop down to lithium, which tends to want to lose electrons. And in losing electrons, right, if it wants to lose electrons, it shouldn't take very much energy to take that away. And so sure enough, lithium has a very low ionization energy. Then we go up to the next element after lithium. It spikes a little bit, but then it drops. Because if you're going to take an electron away from that boron atom, you're taking it away from a p sublevel, leaving a filled s sublevel. So it's not too hard to lose that electron. But then it goes up, and it goes up again. And then right here, after there are 3 electrons in a p sublevel, it drops just a little bit. It's a little bit easier to take that electron away in the p sublevel when what you're leaving behind is a half-filled sublevel. Now, it still would rather gain electrons at that point than lose electrons, and yet leaving a half-filled sublevel makes it a little easier to take an electron away from the p sublevels when there's 4 electrons there than it is when there are 3. And it climbs again to neon, which has a fairly high ionization energy because it's a noble gas, and then we go around to the next element on the periodic table, sodium, and it drops again. And you can kind of see this trend play out. You can also maybe take a look at what's going on with the transition metals after you get past potassium. And notice that they're mostly fairly similar, but we have a little bit of dropping going on there near that filled D sublevel. Okay. On this table on the bottom, we have another piece of information where we're looking at multiple ionization energies. So the first ionization energy is the energy required to take 1 electron. The second ionization energy is the energy required to take 2 electrons, third, fourth, fifth, and sixth. So let's go across this period that they have listed here for us. So starting with sodium, is a very low first ionization energy. These are all measured in kilojoules per mole. Yeah, they are measured in kilojoules per mole. I had to double check the table there. But so sodium has a fairly low ionization energy because it's fairly easy for sodium to lose an electron. It's trying to lose an electron to get closer to the noble gases. But then notice the second ionization energy. Sodium loses 1 electron and it has a noble gas electron configuration. But then notice what happens if you try to take 2. It jumps tenfold. So that second ionization energy is really high, not terribly surprising. So then we go to magnesium. Magnesium would want to lose 2 electrons to get to a noble gas. So its first ionization energy is, again, fairly low. Its second ionization energy is higher. It will always be harder to take the second electron away because after you take the first electron away, all of the electrons are going to pull in a little bit tighter to the nucleus because the nucleus has to hold on to less electrons now. But it only increased by about double. Notice what happens then when you try to take a third electron away. It way more than doubles. It goes up almost 7 times to 7,730 kilojoules per mole. And then look at aluminum. Again, you have a fairly low ionization energy. Aluminum would need to lose 3 electrons to get to a noble gas. Again, we about double to get to the second ionization energy, about double again to get to the third ionization energy, and then boom, it goes from 2,800 to 11,000 in the fourth ionization energy. And we can kind of watch that trend go all the way across the periodic table. Again, notice argon is the highest ionization energy in that period because argon is already a noble gas. Okay, let's move on to electronegativity. Electronegativity is the tendency for atoms to attract electrons. So now instead of making cations, we're going to be making anions. Electronegativity is a little bit different than ionization energy. It's not an energy. There is a corresponding concept known as electron affinity, which is a change in energy as things gain electrons. But the electronegativity is a relative tendency. It's not measured in terms of energy. If we look on the periodic table, the trend for electronegativity is similar to the trend for ionization energy. As you go across a period, you're getting closer and closer to things that want to gain electrons to get to noble gases. So fluorine, for instance, only needs to gain 1 electron. It has a very high electronegativity. It wants to gain that electron, whereas lithium, sodium, potassium all want to lose electrons, so they have a very low tendency. Your electronegativity also increases as you move up a group, because if you're thinking about adding an electron to francium, you're adding it to the 7s. And there is a tremendous amount of electron shielding, so the nucleus in francium is not very sticky for electrons way out there in the 7s. Whereas lithium, would be trying to gain an electron in the 2s, much closer to the nucleus. And so it would be slightly easier to do that, even though everything in the alkali metals would tend to want to lose electrons. Again, ionization or electronegativity, is a relative tendency. It's a scale from 0 to 4.0. Fluorine is the highest electronegativity that you can have. And so with that in mind, if you think about this trend we're looking at here, what can we say about the noble gases? Well, what do we think about their ionization energies? Do we expect them to be high or do we expect them to be low? Well, it'd be very, very hard to take an electron away from a noble gas because they already have the lowest energy arrangement. And so you would expect very high ionization energies. What about electronegativities? Well, they have a very low tendency to want to attract electrons because, again, they already have an incredibly stable electron configuration. One last topic to hit before we wrap this unit up, and that's atomic radii. So rather than particular trends in atomic radii, really all I want you to think about here is relative to the size of the neutral atom, what is the difference in size in atomic or ionic radius for anions and cations. So in this table, the gray are the size of the atoms, and then the colors are the size of the ions. So think about what's going on with a cation. Cations are losing electrons to become positive. So you would expect the cations to have a smaller radius than the elements that they come from. On the other side, anions are gaining electrons. And so you would expect that the anion would be bigger in radius than the atom it comes from. How are these things measured? Well, in a very similar way to atomic radius, but we do these with the crystalline structure of ionic compounds. So here you have represented, the cations would be in red because they would be smaller. The anions would be in green there. And crystallography then would be a method for measuring the distance between the nuclei of these two things. Now, here you're not going to be able to cut it in half, but you're going to have to be able to do a fair bit of data from either known atomic radiuses or you could extrapolate by looking at several different compounds that contain the same ions. But either way, they're able to measure these things so that they get stable and consistent results that are then able to be compared one ion to another. Okay, so that wraps up the physical properties, and that wraps up our unit on the periodic table.